Okay, good evening for our friend from Asia, and also good morning and good afternoon for the rest of you. Welcome back to this RoboCup at Home Education Online Challenge 2021 online classroom. So today we have open platform OP class. We will talk about robot navigation. Okay, so today is the fourth class of this series, and for the first half we will discuss about SLAM map building. So I'm Jeffrey, will be your host and also speaker today. And together with us are a few engineers from Jupiter Robot that will show you some cool demonstration after this. Okay, so this is the meeting arrangement. Okay, so on the top right-hand side is the meeting link. So just in case like any of your friend or your student or whoever still searching for the link, you can just snapshot on this QR code and send to them. Okay, so they can straight away admit to this meeting room directly from this link. Okay, so as usual, we will divide our class into two sessions. So first half 1 hour and also the second half another hour. So first half we will talk about the SLAM map building. So we will show you some tools how to scan the map, a 2D map for a robot to do navigation. Okay, and then following by that, the next session we will show you how to use the map so that the robot able to navigate autonomously on the environment. Okay, inside the environment. Right, so as usual today we will have 2 hours content, so not just the discussion about the theory, we will have a lot of demonstration. And today, because it's navigation, not just in simulation, because we need some physical interaction with the environment, so we will use Gazebo as the simulator to show you this work or the navigation in simulation version, but also we will show you how it is done in real world as well, and also we will show you how to you can do the comparison between these two. Okay, right. Okay, so just in case you still don't know where is the material, so the first link will point you to our main page for our online classroom, which is you can find the time and also the meeting link. And for the course materials, for example, the PDF in front of you, you can find it on the course materials, and also all the videos, including like the videos of this class recording for the past few weeks. They are all within, you can find them in the second link. Okay, just go to the second link and you can find all those materials, including the past assignments and so on. Okay, right. And the third one is just in case if you want to interact with us, you can join our class group so that we can have some interaction online. Okay, so before I start, the last reminder for privacy. This whole session will be recorded into video, and we will publish this video on our website and also some related website for our community for reference. So please refrain from turn on your microphone and also your view cam all the time, except during the interaction period, or you are told to do so, then only you turn on. Okay, thanks for cooperation. So let us start the content for today. Okay, so today we will discuss about robot navigation development system, and because this one is for everyone able to follow the class, so today we will show you how to do it in a simulation way. Okay, you no need to have a physical robot in order to learn this. You just need to have a laptop that install or set up the virtual box that we have provided you in the first class, which inside there it contains the Ubuntu OS, the ROS system. And also today we will use the Gazebo Simulator. Okay, so we already introduced this Gazebo maybe in the first class, but today we will use it and we will show you some brief introduction, what is Gazebo, what is inside there, and how we can build some simple environment inside there, and also how we can do our navigation development inside the Gazebo Simulator. And some other related software, for example, the navigation package of ROS, and also the tools inside there to help you to do the localization and also the path planning and so on. Okay, so these are all the hardware and software that you require. Basically, you just need a physical laptop, and the rest of the software come together with the VirtualBox. Okay, so for today we have these two parts. So the first part, SLAM map building. We introduce you some concepts, simple concept of mobile robot, particularly on the design of the locomotion. And then we will talk a little bit about robot odometry and also the localization. Okay, so what is odometry? What is localization? Then for the second part, we will proceed with autonomous navigation, which is mainly will briefly show you what is the idea of robot motion planning. So how to plan, like for example, you want to go from one point to point A to point B in your map. So you already have the map. You want to go from point A to point B. So how robot actually plan the path from point A to point B, avoiding all the obstacle and also try to find the best path, for example, the most efficient path and so on. And then how ROS actually do the control and also all the underlayer operation in order for the robot to follow a particular path to move from point A to point B to achieve what we call the autonomous navigation. Okay, so basically that is the content for today. Okay, so first half we talk about SLAM map building, but before we want to start with the SLAM part, we need to first understand the locomotion. The locomotion, simple term is like how your robot move. Okay, so for example, like human, we have two legs and then we have certain walking gaits, and that is how we actually move around by using by walking with two legs. And also for robot, we also have two-legged robot, right? For example, like this one. So we have like, for example, the Honda Asimo and so on. We have many like humanoid robots that work with two legs and multi-legged. Okay, multi-leg. For example, a design like animal. I think now we have a lot like the Boston Dynamics Sport and so on. And they have many legs as well. Okay. And also they have like wheel, track, for example, like this design, and also without legs, like it will move like a snake. Okay, omnidirectional crawling, wall climbing. So it depends on different type of requirement in the environment and also the task of the robot. So you design and also sometimes it's inspired by the nature. For example, like you follow certain animal design and so on. So particularly in this class, we are using this very normal Romba style of platform, mobile platform that use two wheel. Okay, and this two wheel is are actually very a bit different from a normal bicycle or normal like Ackermann steering in your passenger vehicle or car. Right, it's normal, it's different. So it is like a two wheel parallel, which is it will move independently left and right, which I will explain more in the next slide. Okay. Right, so in this slide, we show some of the example of wheel mobile robot mechanism. Okay, why we need to know or study about this, and in fact, we need to actually build the model in order for you to know like how we actually do the odometry in order to calculate and all those things, because these things will eventually become your calculation or part of your model in order for you to do your calculation for your localization. Localization is how you want to find the current location of your robot with respect to your environment. Okay, so it is very important for you to understand this concept, but we are not going to go very detailed on this. But at least I hope in this class you can grab some basic concept so that you know how this thing will eventually link to all the underlayer calculation in your localization and also navigation program. Okay, so we have parallel to wheel, Ackermann steering, and omnidirectional. So omnidirectional is like this. So which means like it can move in any direction, all direction. Ackermann steering is similar like your bicycle or your passenger car, which is you have a steering wheel in front and a driving wheel behind, which is they will the front wheel will determine your steering direction, which is your direction of your robots, and then the wheel behind will determine whether you go forward or backward. Okay, but in this class we are going to use a model called parallel to wheel, which is this parallel to wheel, which is like this. So you can see like this, these are the two wheels, and then it connect to two separate motors. Okay, And this design is very popular in mobile robots for tight corners and so on. And you can see, like, I think like almost all the design for floor cleaning robot, okay? Because this wheel is very similar like floor cleaning robot, it uses this design, okay? So parallel to wheel. So over here we have a definition that may be good for you to know. Is like this: holonomic and non-holonomic. Holonomic means x, y, theta. So the movement of your robot is it can be described by these three parameters. X, y mean, for example, you try to imagine it's a 2D plane, because for mobile robot we don't consider the z direction, okay, because it's flat on a flat surface, so only x and y. So in 2xy Cartesian is the direction, and also the theta is the orientation of the robot. Okay, so for holonomic design means these three can be changed independently, which means your robot can move in x direction, y direction, and theta direction independently. Independently means you don't need to change the rest, or you can put the rest of the two parameters static, the same, and you can just change one of the parameters. Okay, so you try to imagine, for example, your bicycle. It is not non-holonomic because you cannot change. For example, like when you turn, you still need to go in front, and then you start to slowly start to change, and everything change accordingly. So it is not independent for x, y, and theta. So that's why it is non-holonomic. And for our parallel to wheel is considered non-holonomic because this one, how to say, it can go front, back, and also turn, but it cannot go in y direction. Okay, when you want to go in y direction, it still need to turn like this and then go x direction, right? So it is non-holonomic, but only this kind of omnidirectional is considered holonomic. The rest, most of the cases are non-holonomic. Okay, and then from this design, actually we try to do the modeling in order to calculate the change. Okay. Yeah. The next slide, we will talk about this odometry and localization. Okay, so now try to put this image in your mind that, okay, this is the robot that you're going to use, parallel to wheel, that it can move two wheel independently, which means they both can turn in different direction. Okay, when both turn in different direction, the robot actually rotate on the same point if the speed are identical, but in different direction. Okay, so try to imagine this model, and let's look at this slide. So odometry is the use of data from moving sensor to estimate change in position over time. Odometry is used by some robots, whether legged or wheel, to estimate, not determine. Okay, so over here is estimation. Okay, their position relative to a starting point. So you try to imagine we have a robot that you know how much this thing turn. Okay, because by kinematic you know how much this turn, and you can actually calculate the distance traveled by this robot. Okay, and when you do this calculation, like how much your wheel turn over the time, and how much this actually change the x and y, and also the theta. So this calculation is called odometry. Okay, so you use the odometry way to calculate the movement of your robot change over time by using the wheel information. For example, like how much it turned over the time, or if you know the speed, because like if you integrate the speed, you got the distance. Okay, so those are the maths that I think you can imagine, but of course you can read more. So odometry, so we use odometry with the model in mind, and also you can get the speed, because like on your motors, you can actually put in encoders to calculate the speed of the rotation. So from there you can do all the conversion and get the distance travel. So you use this concept in order to calculate how much the robot's supposed to move in the environment. And keep in mind that this is estimation. Why? Because in real world, your wheel is going to slip based on different kind of friction. So a lot of errors actually happen. Okay, so if you can calculate, but it is in a perfect condition, which is always not true in real world. So that's why you use this odometry to do the estimation, but it is not very accurate just by odometry itself. Okay, so in order to improve the accuracy, so to improve the Turtlebot, so over here we use the Turtlebot, which is like the base of our robot odometry. So we added a gyro. Okay, so now we introduce another sensor. Just now we have the encoder to find the rotation of the wheel. Now we added a gyro to the iRobot Create, which is the base of the Turtlebot. Okay, so the robot pulls EKF. EKF is extended command filter. So this is a node. A node means a program in ROS that use the gyro and also the odom data. Odom data is the odometry data that you obtain from the wheel to compute and publish the more accurate odom combine. So the odom combine is a combination of odom data, which is calculated from the wheel, plus, okay, although it is not plus, but it's combined with robot post EKF model, okay, that use the data from the gyro. So you have two set of estimation, one from the gyro and one from the odom data. So just now I explained about the odometry, now I explain the gyro. So if you know that our phone also have this kind of gyro, that it actually give you like you can use your phone to track your movement, right? Like how many steps you have moved per days and so on. So actually the gyro sensor in your phone actually use the data, the motion data, and it try to find your distance travel. Okay, so a simple way for you to understand is like gyro will give you, for example, the acceleration of this direction. So if you integrate the acceleration, you will get the speed, and if you further integrate, you will get the distance travel. So that is how that's a very simple explanation, but in practice, it has its own algorithm to do the calculation. But the concept is similar. Okay, so you use the gyro, you get the distance travel, and this set of data combined with the odometry, which is from your wheel. So you are going to combine these two, and how to combine? We use this what we call the extended command filter. Okay, I'm not going to explain command filter, but command filter is a way that you can combine these two series to give you more accurate estimation of the odometry. Okay, so this is how. And if you look at the inside your robot, so you have the sensor that give you all the sensor data, and then you have the robot that, okay, so you have the sensor data, and this is the Turtlebot. So you have two sets of the motion data. One is from the gyro, one is from the odom. And with this algorithm, the robot post EKF, you have the odometry combined, which is the more accurate estimation of the odometry of the robot, which is you can estimate the current position of the robot based on the movement data. So this is how you get the odometry. Okay, so this is a bit more further information. So EKF is extended command filter, so it used to measure the observed over time content, noise, and so on. Okay, so if you want to know more about command filter, you can find a lot of information on the web. And command filter is a very how to say, popular tools in this motion estimations and so on. So if you would like to know more, yeah, you can find a lot of resources online. But basically, we use the same thing in our model in order to get the localization of the robot as well. Okay, right. So now talk about localization. So you understand the concept of odometry. So the next thing you need to know is this localization. So localization is the robot localize itself using odometry and laser scan data. So just now you know, like odometry, you use two sets of data. Now we have another set of data, which is from your laser scan. So from last week class, we learned about the Kinect sensor, right? So you know, like there is a 3D scan in front, and then we also have the distance sensor, which is, it will give us something like the laser scan. So laser scan not usually come from the LiDAR, which is it use laser, but for the Kinect, it also use optics, which is like it use the infrared to give you something very similar like laser scan, but with less accuracy. Okay, but the concept are similar. Okay, so you get the laser scan data. So you are going to use these two data in order for your robot to do localization. Okay, so the right image over here. So this one, you try to imagine this. Okay, so this one is something very similar like a living room. So if you look from top, you will see something like this. So this is a long sofa. This one is the two-seated, and then this is a one-seated sofa. So it's like this. And then this one got 4 dots. But instead, if you look from top, it's supposed to be a table. Why like this? So if you look at the robot, the sensor is actually about this height. So if, let's say, you cut the plane, based on this height, you cut a plane. So for the table, actually is somewhere over here. So which means the cross section that you cut, what you can see is actually the leg of this coffee table, right? You got 4 legs for this coffee table. So you got this cross section. So the laser scan actually give you a particular height. That particular height, it gives you the plane, how it looks like if you can have the cross section look from the top. So basically that is, if you cut this thing out and look from the top, that is basically your 2D map. Okay, it looks like a 2D map if you do the laser scan on this level. Okay, so the right image show a map. Okay, the image on the left with the robot localized with laser data overlay on the map. Okay, right. So the gray area of the map show the unobstructed area of the map, while the black show the obstructed area. So obstructed and obstructed means the black area are the areas that the robot cannot enter. Okay, the gray area, which is like all these spaces, are the places that the robot can go in, except this one. Okay, the robot cannot go in here, which is this is the thing that you need to be careful when you build the map. Okay, we will explain more about this later on in the actual practical of map building. But over here, please keep in mind that when we use the laser scan to try to get this map, this is the things that is going to happen. Okay, because you need to know the height of the sensor that are not going to give you the 3D scan from bottom to top, but it just gives you one slide based on one particular plane. Okay, so this is how we try to get the map. Okay, so in Turtlebot, so it combines. So just now we have this model. Okay, so now we add in one more information, which is from the Kinect, which is from your RGBD sensor. Okay, so come in here. So with this, we are going to use a tool called AMCL. Okay, AMCL tool, which is stand for Adaptive Multicolor Localization, which is a tool that we are going to use it for our localization. And for this AMCL to work, it required the scan from the 3D sensor. It required a map, which is the map that you built just now in the SLAM. Okay, just now. And also the TF. The TF is the transformation function. Okay, so which means the 3F actually explain the relative position of all the component in ROS. Okay, or in ROS. Okay, so you are going to use this in order to find the new TF, which is the new position of your robot. Okay, or the position, the localization. Right, so the OpenNI manager, which is the Kinect, use the point cloud data to create the laser scan, so as I said, and then for the use of AMCL. So AMCL use the scan and also the ODM combined to compute the transform from the map to base link. Okay, so it is the relation between the base link, which is the base of the robot, and also the map. So how it actually change. Right, okay. So this AMCL, Adaptive Multicolor Localization. Okay, this concept might be not easy to visualize. Okay, and maybe like after I explain, you might still don't understand. But if you look a few more times, and also later on in the practical, you might discover the point, and then as you go on, the point get reduced, and eventually you get accurate estimation. So how it works? So this AMCL works by figuring out where the robot needs to be on the map in order for its laser scan to make sense. Okay, so try to imagine like if your robot got a laser scan, which is like it scanned around and give you the information, and you have this information, so you try to find in your map which location the robot's supposed to be in order to match with the scan. So you know the scan, okay, and you know the map. So AMCL is try to use the particle filter method to find, like, if you have this scan, which location in the map supposed to be so that you can have that particular scan. So that is the concept. So maybe in the first scan, you only have like one scan, you have maybe like many possibility for your robot to be on the map in order to match with the laser scan. So you will continue scan and do this comparison, and as you go, those that not, how to say, those that not matching the particle will be eliminated. So eventually you will reduce this particle until you only have left one possible location, which is will match all your scans. So that is the correct estimation. So the process of this thing, what I just said, is used in AMCL in order to find the location of the robots. Okay, right. So yeah, in simple terms, like each possible location is represented by a particle, and particles with laser scan that do not match well are removed. Okay, resulting in a group of particles represent the location of the map, the robot in the map. So later on in the practical, you will see, like, when we try to estimate the location, we will see a lot of small arrow. And when we move the robot, the small arrow will reduce, okay? And eventually you will get the correct estimation. So that is the concept of AMCL. Okay, so we are going to, so I already done most of the explanation. So we are going to see how to build the map. Okay, but before build the map, let me introduce to you those tools that we are using. So first is like we use this OpenSlam G mapping. Okay, so in normally it is known as G mapping. So G mapping is a tools in ROS navigation for us to build the map, right? We are not going to like discuss or explain how G mapping build the map. If you are interested, you can refer to the website to see more further information. But over here, we will show you directly how we can use G mapping to build the map. Okay, so you can just go to this site, and it has all the command to show you how to build the map. But I'm going to leave this demo to our colleague in Jupyter Robot, and he will show you this after this. So let me finish all the explanation, then you will see the demo. Okay, then we also need to have some brief introduction. Later, I also want to invite David to explain more the Gazebo Simulator, because like he's going to show you the interface and so on for more introduction. But over here, I just do a very brief one. So this Gazebo Simulator is it simulates the 3D rigid body dynamics, the dynamics of the robots. And please don't confuse Gazebo Simulator with your RVs. RVs is basically just a virtualization of your sensor data. Okay, it is not a simulation. But Gazebo is a simulation, which means you have your model, you have all the dynamics rules inside there that will interact with each other to show you how it looks like in a simulation. Okay, so it simulates sensors as well. So you can have your 3D sensor and all those things being simulated in Gazebo, and then you can create your environment and also your robot, which is what we call the Gazebo worlds. Okay, it provides the ROS interface, which means the robot can actually be controlled using ROS. Okay, right, and how you want to run your Gazebo, basically this is how you want to run your Gazebo. Okay, if you have more information, you can go to the website to have a look. So later on, David will introduce to you these tools and how we are going to use this Gazebo Simulator for our navigation today. Okay, right. So we are going to use our base, which is what we call the Turtlebot Tool. And we already have the simple model in Gazebo, which is later on maybe David will show you a more advanced one, which is a Jupyter Robot. But yeah, they work similar in Gazebo. So we have the Gazebo environment, and then we have the sample. So don't worry about the environment. If you want to know more information, you can go there. But later we will show you the model or the simulator model that we already have in our VirtualBox. Okay, and this is how you bring up. You do the ROS launch and then Turtlebot Gazebo, which is the package, and then the world. Okay, and you launch and you will see. Okay, Okay, I will leave all this operation to David after this. I just tell you what you're going to expect. So in the simulation, what we do, so first we launch the G mapping for map building. So once you have launched this one, you already have the gazebo with the environment and also the robot model. Okay, so you try to imagine you have a virtual form of the environment and the virtual form of your robot. Okay, because you don't have the real one, so we will work with the virtual one. Okay, so once you have this, so the first thing is in that world, you are going to start build your map. Okay, so now our first objective is to build the map. It's not autonomous navigation yet. We just want to build the map. Okay, so the first thing is we are going to launch the G mapping for map building. So over here you can see we use inside the Turtlebot Gazebo package, we have the G mapping demo. Okay, so we can use the G mapping demo, which is we'll launch the G mapping tool for you to do the map. Then we are going to use the RVs to see how the map is being built. Okay, because the RVs will show you the sensor data, and where the sensor data come from the virtual world in Gazebo. So which means we use the virtual world robot to use the virtual sensor inside there to do the scanning of that virtual environment, and this data will be feedback into your raw system, and it's going to show you how it is built. The map is being developed in RVs because RVs show you the visualization of the sensor data. Okay, then you need to do this few operation, which is you need to like change the topic in order for RVs to update the data. Okay, then you are going to use the teleop to move your robot in the virtual environment. Okay, so this is the teleoperation program in ROS that used to control your robot so that your robot can move around. So as the robot moves around, it will scan the environment and feedback the data, and you will use this data to continue building the map until you finish the whole environment. Okay, then lastly, you will save the map. Okay, so basically this is the procedure, but don't worry if you are lost now, because like you are going to see the steps after this. Okay, step by step. And one thing I would like to say also is our simulation development here, we actually have one more model, which is we have this example that model in Gazebo with an actual similar model in real world. Okay, so this one is the Jupyter Robot office. So they have a test field in the office that they built up, and they provide us with the Gazebo model that have the one-to-one scale. Okay, so if you open this thing in your Gazebo and you do some development over here, you can actually use the same program on the Jupyter Robot on the same environment, and it works identically. Okay, the navigation will work identically. So over here, we actually have a realistic simulation environment for service robot development, which this demo will be shown by David after this as well. Okay, and also our engineer in Jupyter Robot. Okay, so before I pass this to Jupyter Robot, I just want to say, like, the first half, we are going to show you the Gazebo, how we build the model, and then how we actually start to build the map in the simulation world. Okay, for the navigation, for the autonomous navigation, and also for the real robot, we are going to do it in the second half of the class, which is after this. Okay, so first we show you the Gazebo and also building map by using Gazebo. Okay, so with that, I would like to invite our engineer, David, and also Max from Jupyter Robot, and also Xiao Huang maybe, to show you how to do this in the operation. Okay, so in the VirtualBox. Okay, so David.
Hi, Jeffrey.
Okay, so I'll pass the screen to you, and you can show the Gazebo and also the building map in Gazebo. Okay.
Okay.
Thank you.
I have show my screen to all of you. Can you see the screen of the VirtualBox? Okay. Now I will show you the how to build map in the Gazebo world of Jupyter Office. As mentioned by Jeffrey, we have already set up the environment in the Gazebo according to the real environment in our office. I will show you the how to launch the Jupyter Office Word in the Gazebo. So there is a little difference with the command in the PowerPoint from Jeffrey, because we have set up our own Jupyter Gazebo package and to launch the Jupyter Word. So the command is here, rows launch Jupyter Gazebo, Jupyter Word. But we have to specify the Word file according to the folder. The Word we have stored in the system is at here, Cat King workspace and words. So you can see there was there were two words here. So the Jupyter Office room is a Jupyter Robot Office is the environment we build according to the real environment, and the Musta room is another room. So I will use the Jupyter Robot Office. We have to specify the folder name, folder path. Pass here and now we start the Gazebo with the Jupyter Office room. The launch file will automatically start the Gazebo Word. So we will show you the word here. And in the Gazebo Word, in the Gazebo software, you can use the left click to drag the thing, and you can use the view to zoom in and zoom out. And if you want to turn the view of the angle of view, you can use the to click the middle button of your mouse and to change the angle of view. And this is the Gazebo Word of Jupyter Robot Office. And now I will show you the real word here. Can you see the real word here? This is a Jupyter Office room, and we set up the examination environment for the RoboCup at home education. So as you have seen in the PPT of Jeffrey, there is almost the same. They are almost the same. I can show you a result that if we build the map in the Gazebo Word, we can also copy the file to the robot, to this real robot, and the robot can use the file of Gazebo Word to navigation in the real world. Okay, I will show you how to how to build the map in the Gazebo Word. And we need to open another tab. Rows, launch, Jupyter, Gazebo. I will use the RP equipment, which is a laser radar to set up the map of the Gazebo Word. Mapping demo. Okay. The command is different with the PPT because we have set up our own package, Jupyter Robot Gazebo, and the launch file is RP radar Gazebo mapping demo. So if you see that registering first scan, that means the program is working well. And the third one, Turtlebot Office launch, view navigation. Okay, this launch This launch file will start RVs to show the result of the mapping. Pay attention to the topic here in the map. which is we have already changed the setting because, for example, for the coast map, we have already changed the topic to the map, and for the global and local map, we have already changed the topic to the map. Okay, now I will show you how to build the build the map, and we can make this window a little smaller. And you can also drag here to rotate the map, and you can use the use the wheel of the mouse to zoom in or zoom out the map. And if you want to drag, you need to use the middle key, middle click to drag the map. Then we can move the map here smaller. And then I will start the remote control. We use the Rose launch Turtlebot Teleop keyboard. There is several command here to show you how to control the robot in the real world or in the simulation world. So you can use this 9 keys. There is a example to show you how to control the speed. And if you want to move the robot forward, you can use the I key, and the K is to stop the robot immediately. And this command is to move the robot back. And this is the turn left, turn right. And this is the U for turn left while move forward. And the O is turn right while moving forward. And we can see in the Gazebo world, our robot is looks like the real robot very much. And we can use the same command to control the robot in the real world. Okay, let's start. Pay attention. If you want to remote control the robot, you need to keep this window on the top of the other screen. If we like this, I can't use the keyboard to control the robot. So we have to show this and click here to make sure that is the active window. Okay, let's start. So for mapping the world, you need to drive the robot move around in the Gazebo world. If you want to build a map, I suggest you to drive the robot. For example, in this room, you need to drive the robot along the wall or along the furnitures, and drive the robot to the original point to make that is a circle in the room. You cannot speed too high to while build the map. It's much better for you to drive the robot slowly. Okay, this is the first map of this room, and I will drive the robot to another room.你去开那个机器人的，把那个窗口打开吧，把5号的那个准备一下。So you can see that in this window, we have more and more map with the explorer of the robot. So this robot uses laser, radar, RP radar to scan the world environment. So I will drive the robot here, the smaller room. Okay, turn around, move to another room, the last room. So if you want to drive the robot a little fast, you can use the Q key to accelerate the speed. Not too much, just a little. Turn around to scan all the direction around the robot and go back to the start point. Pay attention if the robot very close to the wall or the obstacle. Please do not hit the wall or the obstacle. This will affect the accuracy of the map very seriously. Okay. Almost done. So you can see here we have set up the map of this environment. And the last step for the mapping is to save the map. So we can use this command, run map server map saver F, and the folder you want to store the map. For example, I will store the map here. So we have set up a folder here to save all the map here. For me, I will store here, for example, test 3. You can see that is the procedure to stop here, and you can see the map here. It's just like we have just set up the environment. Okay, that is the procedure to set up the to build the map. I mean, mapping in the Gazebo world. Jeffrey, do you want us to show the real robot to how to build the map?
Yes, since we have time, yeah. If you can show in the real world, will be good.
Okay. I will show you the. Get ready? Are you ready? 我开你看，我开着你看那个画面。我来吧。Okay, this is the robot we will use to build the map, and this is the screen of this on the screen of this robot. For the real robot, there is a little difference with the command here. So I will show you. I will drag a little large. Rose launch. Sorry. Rose launch Jupyter robot bring up. Jupyter robot bring up. 开电了吗？ Rose launch Jupyter robot navigation RP radar G mapping demo， 对吧？ RP radar， RP radar G mapping demo， OK， here。 Yeah, Adobe received, and I will launch the Avis Turtle. View navigation launch. Pay attention to the map here. We should change the topic to map This is local map, and this is the global coast map. Okay. And for the real robot, we have already set up a new remote control method. We can use the joystick. 看不到，你放到那个机上。We use this joystick, which is a Logitech gamepad F710. F710. 好了 ，Close launch. 你可以站在这个边上，一会儿我会给你画面。啊 ，Repeat robot teleop move， 对吧 ？Repeat， 不对 ，joy move。Okay. So for joystick, we can minimize size this window, and we can use the joystick to control the robot to move around the world. Okay, you can start. 可以了，开始吧。可以。So because this is a real robot, so you can see here we cannot find the size of this table. We can just scan the leg of this table. That's the difference between the real world and the Gazebo world. 你可以往那个跟前，你可以走快一点，用快速走，正常速走没关系。对，可以的。对，然后去这个空间。So the power, I mean the ability of the real lidar is almost the same as we simulating the Gazebo world. So you can see the procedure is very similar to the Gazebo world. 先绕着沙发转一圈。So for this table, there is also the same problem that the real robot cannot see the top of the table. They can just scan the leg of the table. So there is 2 points here, not the table. 进小房间，然后回到你的起点就好了。这里面转。对。里面有机器人呢，退回来，出来就行。我准备存图了，你回到起点就好。So the robot will go back to the start point. Okay. And we'll use the same command to save the environment, save the map. Let me check the name. Maps test 1. Okay, test 2. Test here. Test 2. Okay. Now I will show you how to solve the problem of the mapping. Just showing the image, which the table. Table is not look like table. They just look like 4 legs here. So we have already installed the software of GNU image process software. We can use the this software to connect this 4 leg to the table. So we can use this one, the pen, and not too much large. Oh, size 2. 2 pixel, and we can, 哎，哪个是笔来呢？我忘记了吗？哪个是笔啊？我现在要画这个，我画这个点，我用什么来用笔呢？我记得是这个呀。哦，不对。但是盘子点了没用。Brush， 不对。Sorry, this is not the. We have just use the image view, not the GNU to open the file. GNU. Yeah, okay. We can launch here and use the pen to connect the. Oh, sorry, just one. Much better. Collect this to make this look like a table, and this one here. Okay. And then we need to save this result, but we can't use the save as. We need to use the export as. Use the same name to overwrite the map. Okay, replace export. Okay, close. Discard change because we have already saved the map. Take a look. Okay, we have just make this look like table. Okay, Jeffrey, that's a demo. Thank you.
Okay, thank you, David. Very interesting demonstration. Right, so let me switch back to my screen. Okay, so I hope you can see my screen now. Back to my slides. Okay, so let me summarize what we have learned in the first class, and also what you have saw in what we've seen in the demonstration. So today we talk about navigation. So before we able to do the autonomous navigation, the first thing you need the robot to do is to build the map. Okay, you need to use the laser sensor or the RGBD sensor that give you the laser scan, and you are going to we use the AMCL package, which is just now I explained in ROS. So these are a few things that we put together, and then just now you saw the demonstration how we actually control the robot, which is having the sensor on top of the robot, and we try to scan around and using the AMCL package to somehow stitch them together. Then eventually you will have the 2D map, which is in a 2D occupancy map. Okay, occupancy map means you have the black and white and gray, actually black and white and gray. So the white color means a free area, which is the robot can pass through. The black, which is considered the obstructed, which is the robot cannot enter the region. And also you have the one in gray, which is the robot is unknown to the robot, which means it is not yet scanned. So I'm not sure whether it's a white or black color at the gray zone. Okay, all right. And also, just now David showed you two versions. One is building the map in the Gazebo, and also another one is building using the real robot. Okay, so in the second half of today's class, we are going to show you like how we are going to do the navigation. Okay, navigation, which means you in the map you specify where is the starting point, point A, and the goal point, point B. Then the robot will use the path planning to plan a path, and then use the control system to control the robot move one by one step by one step, until it reach the goal. Okay, so that will be the second part, right? So So basically, that is what we have seen in the first half. Okay, so let's go to our exercise, okay, or assignment, right? So come to this page, you can click over here. Okay, just a reminder, like the video for last week already up, it's inside here. So now if you click inside here, you can see like our slide for today. Straight away we go to the assignment, okay? So we have, again, the similar, we have the assignment for the first half and also assignment for the second half. So the first half is very simple. So all you need to do is exercise on the SLAM map building. So what you need to do is just repeat whatever that you have just seen in the demonstration just now. So build map of the example environment in Gazebo. So you can use the Jupyter Office, or you can use the default one as well, right? The Turtlebot one as well, also, or whatever example that you can find in Gazebo, you can use. Or even if you want, you can actually build your own environment for you to do the mapping as well, right? If you want to know how to build, you can study more on Gazebo, how to build a simple boxes within the Gazebo. Then you can put the model in so that you have the environment. Okay, but this one is just for exercise, so you can just do the same like what David have shown you. Then the second one is the post-processing map. So just now David also show you this example, post-processing map with graphic editor software, which is just now David show you using the GIMP, okay, which is already like pre-installed in the VirtualBox. So what you do is like you open up any graphic editor software that can support that particular image file. So you open up, and all you need to do, because like the file actually is just a black and white image file, okay, it's nothing how to say, nothing complicated inside there. So what you need to do is you open up with a graphic editor software, and then you try to darken those areas that you know are the areas for the obstacle. So for example, just now David tried to connect the 4 leg so that you have the whole area darkened. Okay, so you can how to say, you can fill in the whole square with dark color, black color, so that the robot will know that particular area is not accessible. Okay, and that is what you need to do. And not just that, but you can actually use the graphic editor tools to actually improve certain things. For example, like if you are using an RGBD sensor to do the scan, maybe your edge is not so sharp, or maybe got some white dot inside there. So what you do is you can add a bold black color line so that you have a very clean wall. And the better your image, or the better your map according to the real world, it will actually help in the path planning later on. Okay, because like if you have a lot of unknown area, for example, like if you didn't enclose your map, you have some part that you are not scanned and it is actually open, and then out there are all the gray zone. So that kind of information is very bad for the robot to do the estimation in path planning. Okay, so in order to avoid that, try to enclose your map by complete your scanning in one circle to make sure everything is covered. Even if you have a door that open, right, you try to cover the door area as well. If you don't want the robot to go out from the door, you just want to know like there's an opening there so that the robot can go out from there, but not going to do anything outside. All right, so these are a few, but I think like over the time you will gain more experience and see how your robot actually interact with the map you build. But a key point here is the better your map, the better navigation, or the more accurate and the less error you will face later on when you use it for your navigation. All right, so for this exercise, you just need to determine a few waypoint flows. So for example, like just now for the Jupyter Office, maybe in a few corners you can put certain waypoint. Waypoint means the name for that particular point that you want. For example, if you have a floor plan for your house, you can mark like this belongs to the kitchen, this belongs to the living room, this belongs to the bedroom, and so on. So identify this key point, and later on you are going to see how we want to specify this waypoint, get the coordinate so that we can do the navigation. Okay, but that will be the second part. For the first part, the assignment, please repeat what you have seen in the demo so that you can get familiar with the interface and also the operation. Right. Okay. So with that, I would like to move to the second session. Okay. So let's move to the second session.